So first of all, thanks for inviting me to talk here. I heard the barrier is really low, so I should do fine. So maybe it's just quickly about me, so why you should care what I say. So I'm Pekka. I'm a founder and CTO of a company that's trying to bring SQLite to the edge. And if that doesn't mean anything to you now, hopefully by the end of this talk it does. I'm also a PhD candidate at University of Helsinki. If you want to know how smart it's to do a PhD and found a company at the same time, don't ask my supervisor. So I have background in operating systems, distributed systems, and databases. I have also, of course, done backend work as well. I was a Linux kernel contributor, and I worked for 8 years for a distributed database called ScyllaDB, which is essentially a Apache Cassandra compatible thing. So the topic of today is beyond cloud computing, and maybe I'll start with raise of hands. So who has used serverless? Who knows what edge computing is? Who knows what sky computing is? So good, there's at least something new. So basically, I'm going to first do a quick primer on cloud computing and a little bit taking like a systems programming perspective, like what is under the hood. And I'm going to use that as a motivation for why serverless and what do I mean that it goes beyond the machine abstraction. Then I'm going to talk about edge computing, which is basically about getting closer to the user. And just quickly, it's like an emerging thing in academia called sky computing, so infrastructure above the clouds. You can think about how's that related to systems programming, but hopefully it makes sense. So cloud computing. So cloud computing is a paradigm where compute resources, CPU storage, and others are available on demand. It's a mainstream paradigm. I don't know how many of you, have actually lived without cloud computing or developed without cloud computing. When I started out, it was actually really typical that you'd have those hardware boxes at the office and so forth called on-premise computing, basically purchasing and operating your own hardware. And cloud computing actually has roots back in the 1960s with time-sharing machines, and this shows my interest in computing history as well. And the key enabling technology for cloud computing is something called virtualization. It happens across the stack. And please, by the way, if there's any questions, feel free to interrupt me. So what is virtualization? It's a technique for creating a virtual interface. So basically an illusion of some physical interface. And if that feels abstract, for example, a virtual machine basically virtualizes a full physical machine. So the CPU, memory, storage, virtual network virtualizes the network, and so on. So it's about creating another layer on top of the actual physical hardware, but keeping sort of the contract to applications machine-like. And hypervisors and containers are basically the main virtualization techniques used in the cloud. So just to run quickly through what hypervisors are. So there are a system program that provides that virtual machine, and it has the aim of basically giving an illusion of physical hardware. So for example, a hypervisor could provide the illusion that it's an x86 or ARM64 machine. And in theory, applications don't know that they're running in a virtual machine. But if any of you has actually run stuff in a virtual machine, you know that there are things that leak through. But nonetheless, that's the model of hypervisors, and they were actually invented in the 70s by IBM, of course, and then reintroduced by late 90s by VMware. And if we get a little bit into what's happening inside a hypervisor, it consists of two components: a virtual machine monitor that basically provides the CPU and memory virtualization, but also something called device model, which provides the I/O device virtualization, so disk and memory and network as well. So if we look inside an example where we have at the bottom we have hardware, then the second layer is hypervisor, and basically on top of this now on that one hardware we have two virtual machines where you have your application and a guest kernel. So in this case, the virtual machine is actually pretending to be a real machine. So there's also an operating system, the guest kernel. So it could be, it's Linux, almost always probably, but nonetheless, And this is going to be interesting a bit later. So just keep in mind, this is the basic model of virtualization, which basically enables the cloud. And basically, so why you want to do this multi-tenancy is obviously a thing. So now on that same hardware, we actually have 2 machines and so forth. So it's also sort of a cost optimization in a sense. So containers. Containers emerge as a lightweight virtualization technique because these things, hypervisors, were seen as heavyweight, and to some extent they are. So Docker is probably the most popular container tool, but it actually builds on 2 features in the Linux kernel. So C groups and namespaces, and sometimes containers are referred to as operating system virtualization. And Kubernetes is basically orchestrating containers at large scale. And they emerged in the early 2000s. Various different container technologies existed, but basically Docker just made the Linux variant popular in 2013. I think it was created in 2013. So what does a container-based virtualization look like? So if we quickly go back, here we had this thing where it was emulating a real, the hypervisor was emulating a real, well, not emulating, virtualization a real machine. In the case of containers, you just run the applications on top of a shared kernel, which uses the namespace and C group. You get the same thing. I don't know if I have a, yeah, so you get the same thing basically, but more lightweight. On the other hand, you trade off isolation, because now you can imagine if the kernel here has a security bug, for example, all of the containers are affected. So enter lightweight hypervisors. So micro VMs are repopularizing hypervisors to address container challenges and isolation. So it is this cycle of things. But as I mentioned, containers have this isolation. It also has a sort of a performance isolation issue as well, because it's much harder to make sure that, for example, application 1 gets its fair share of the CPU. The C groups subsystem in Linux attempts to do that, but it's super hard. So basically, what people came up with was, can we make the hypervisors more lightweight? What is interesting is that a lot of these tools, so Firecracker is basically the most typical one, came from Amazon. So what is interesting about this is that actually you usually can run a full Docker container. So it works with the Docker container. You don't need to do this heavy image building that people usually associate with hypervisors. And basically it's the same model, right? Nothing changed here. It's just that the hypervisor layer is optimized. And now what does it mean that it has an optimized device model? So basically there's a lot of other optimizations they do, like to reduce boot time and so forth. So basically they give up the illusion of a real machine. So in the first slide I was showing the first generation of hypervisors that, for example, could boot Windows. And that basically means emulating the whole, 30, 40 years of basically IBM PC architecture. So the boot time, the bootstrap process, if you haven't looked into it, it's super fascinating, because it's basically when you start up your machine on a PC, there's a lot of different things that it does just because of history, right? Because they still can basically boot MS-DOS, a lot of them can. Well, there's now new stuff that doesn't, but basically this is what the lightweight hypervisors do. Let's get rid of that and optimize the device model. So basically original hypervisors also basically emulated some specific hardware disk or memory, network controller. So what they did is, let's create virtual devices that are as efficient as possible. Basically the issues around moving data back and forth between the hardware and the virtual machine. So finally, this is the final thing on cloud computing. So unikernels. So unikernels are an interesting optimization where they fuse, actually I worked on a unikernel in the past as well. So you fuse your application and the kernel code. And these unikernels combined with micro VMs allow really fast application startup, suspend and resume, for example. And they emerged in the mid-90s, but actually around the same time as Docker, the first unikernel appeared called Mirage, and they sort of got lost, Docker won. But now because of this wave back to hypervisors, they are emerging. There's a project called Unicraft, which is showing great promise. So what are unikernels? If you remember, the first slide looks really similar, but now there's no guest kernel. So you pack the application code and the kernel code into the same. And it creates some, it's an optimization that makes some things efficient. You just have to believe me or go check it out yourself. So that was the primer on cloud computing. And basically, what we saw was this everlasting trend to be more lightweight. And arguably, once you get to the final stage of unikernels and imagine a lightweight virtualization, where do you go? And basically, you go to serverless. So you drop the machine abstraction. So serverless is a cloud computing paradigm, which is built around the concept of functions instead of machines. Right? So applications are composed of collections of functions which do something, perform some action. And there's a serverless platform that executes the functions. It's called function as a service. A really typical case is, you have a REST API, you get some HTTP requests in, and you send some HTTP responses back. And why do you do this? It has the same kind of motivation as in cloud computing with hypervisors and containers, so multi-tenancy and cost. So because serverless is also virtualization, but at much higher level than a machine, so it allows much higher multi-tenancy and therefore lower cost. We will get to the cost part when we go to edge computing. And for example, Cloudflare Workers, I don't know if people have used it, it's a serverless platform which basically runs your stuff on a V8 JavaScript WebAssembly runtime. It's the same thing that runs on the Chrome browser, for example. And it lets you run more than more applications on one machine compared to containers and micro VMs. But there's a trade-off on isolation. So if you think about how you would, in a cloud computing or a machine-based paradigm, how would you go about deploying your application? So V8, maybe Node is better here, but nonetheless, Node uses V8. So what you would do, you would create virtual machines or containers where you have your application and you have your runtime. But in case of serverless, and this is probably a typical, or at least was in the past. But this is basically what you do, right? Now your function is just one of the functions that the serverless runtime runs, right? And the isolation trade-off here is that I was talking to Cloudflare engineers, and they just mentioned that whenever there's a V8 security bug, people are quite busy because you now have to really quickly not just patch it, but basically redeploy all of these functions, because as long as V8 has a bug, there's a potential that one of these because V8 is enforcing the isolation, right? It's easy to think that because these are your functions, like what possibly bad things could they do? But actually they can, because they just run. So if they can trigger the bug in V8, you could, plausibly, for example, read someone else's function state. So what is the programming model? So a lot of people raised hands about serverless, so I'm just going to run through this quickly. So again, you define your application as a collection of stateless functions. HTTP request response is typical model. I'm going to give two examples. Cloudflare Workers. So you create an event listener, which is actually an HTTP request, and then you handle it. And this is like the simplest case where you just actually ignore the request and send it back, right? And the same thing with AWS Lambda. I didn't actually run this in production, so I don't know if it works. But super simple, right? But the trick here is that now this is the thing that created the higher level of abstraction. Like you don't care because this is the description of your application. You don't define a Docker image saying that I need this runtime, I need that library, da 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 da. This is the unit of deployment. Is this clear? I hope so. So, but what about state in serverless? So I mentioned briefly that serverless is all stateless, and you can imagine why, right? Because when you have this thing, one of the reasons the cloud providers really love this model is because they can, your function is just one of them. You could, like I only put 12 here, but it could be hundreds, right? So it's super great, it's super scalable. But once you introduce state, it's not so easy, right? Because state is much bigger than the compute requirements. So it is actually not a fully solved problem yet. Key value stores and caches are typically used. Sometimes you use a cloud database, which tend to have high access latency and also high cost. Serverless databases are emerging to solve this problem. A lot of companies are working on this, my company included. So that was serverless. So next up, edge computing. Getting closer to the user. So what is the edge? So it's a paradigm that moves compute and then perhaps state closer to the user at the edge of the network to reduce latency. And whenever I talk about edge computing, people say it's a buzzword. And usually I just say, when I say edge, I mean fast, right? But there are two, and it's an ambiguous term, we'll get into that. But there are two main definitions, which are the near edge and the far edge. So near edge is typically when people in the industry at least talk about edge computing, this is what they mean. So it's compute and state that's located somewhere between cloud and the user, but still in a data center. So still a bit ambiguous, right? But the point here is that it is not on the client. It is or not on the base stations, for example. It's in the data center. And near edge really has its roots in the content delivery networks that basically popped up in the early 2000s to, well, not just serve static content such as HTML, CSS, and so forth. Also, big files was, I think, actually the first real use case, right? So this is an example of where Cloudflare has those data. So these are all data centers, right? And I should have had another diagram showing, for example, AWS data center locations. But the running example I use is there's a AWS data center in Stockholm, which is 20 millisecond round trip or something like that. There is a data center by Equinox, maybe 2 kilometers from my house. That's near edge. That's where I would want my request to be routed. Far edge, I hinted towards this. I don't think these solutions have really converged yet. So for example, far edge is further away from the near edge, right? Somewhere between the last mile. So AWS Wavelength, for example, provides AWS storage and compute in 5G networks. Never used it. An interesting thing is that the thing that I said was a thing of the past, so on-premise computing. Now it's also far edge. So Microsoft, Google, and AWS all provide the ability to run their infrastructure management software, but on your hardware. And actually, there are use cases where you want your own data center close by. We could have a rack here, but it was running all day. It would be essentially an edge location in Microsoft or Google or AWS service. And Internet of Things, I'm not really going to talk about it, so all these sensors and devices, but they could also be considered to be part of the far edge. And actually, if you go and talk to academic researchers, for example, it's usually a good idea to figure out which edge you're talking about. So here's the question, is edge serverless, right? So edge locations are really great for low latency, but they can be costly, right? Because the reason AWS has these huge warehouses of compute is because they have the economy of scale, right? You basically run a single big farm of machines. But these edge locations, they're much smaller, and as people, more and more people want to use them, of course, something has to give, right? So they can be costly, which is why you need multi-tenancy. So unsurprisingly, there's some conversions between serverless and edge platforms because they're a really good fit. So one example is what I tend to call programmable CDNs, because I think that's a better name. They often refer to themselves as edge platforms, right? But over the past few years, platforms like Vercel and Netlify have emerged as a programmable CDNs, essentially, because they provide you with a model where you can do server-side rendering, right? Generate that HTML close to users. So instead of serving static content at the edge, you can actually render static content at the edge. But actually, these platforms are now providing what they call edge functions, which are essentially serverless functions on the edge. Local first, it's not, well, so local first is a new movement, relatively new movement. In the industry, often we call it offline first. So it's a way to write applications that actually run on the client, no networking needed. These things existed before, but this really cool trick that they are now using is something called coordination-free data types. I'm not going to get into them, but basically they allow like collaborative applications, for example, to be written because you don't have to be constantly have a network connection. And it makes a lot of sense because if you, for example, are on the train, as I was coming here, the network can be spotty, right? So in real world, networks go up and down. Wi-Fi goes up and down. There are some frameworks that exist. I don't think an ecosystem has really developed yet. They're often used, with a cloud data store for persistence. But it's an example of the edge thinking of getting low latency, but this is sort of the extreme case where you put it on the client. So does edge matter? This is actually a question people ask me almost always when I mention edge computing. So does it really, edge computing claims lower latency. Does it matter? My answer is yes, because there is this trend towards always-on applications with, real-time experience. It's an ambiguous term as well, but basically the ability to, people not really notice the latency, and we can actually quantify. So this goes to the human perception, which I absolutely don't understand anything about, but I do understand enough to read the studies where basically this is like a really rough ballpark number. But after 100 milliseconds, we people actually start to perceive things. Like if something is sub 100 milliseconds, to us it's more or less instant, right? And now, when you think about what is the geographic latency between New York and London, for example, it's already 60 milliseconds. And this is actually a case where the high-frequency traders pay a lot of money to get that low latency. In reality, it's going to be closer to 100, maybe 150 milliseconds, right? So if you now need to do more than one round trip, it becomes a bit difficult to be in the hundreds of milliseconds range, right? So edge databases, right? So if we already have compute at the edge, and we mentioned that serverless, key value stores and caches are used, what about the database? And this is a disclaimer, I'm working on one of these. So if you don't trust vendor benchmarks, and you shouldn't, I don't, so close your eyes and ears. But in any case, and I'm not gonna name it, the edge one is what we do, but basically, let's look at what does the edge data latency look like. So Vercel created this benchmark. Actually, they released it last week, I think. It's a really great way to basically illustrate why any of this stuff matters, right? So here's a cloud database. This is a copy paste of the Vercel benchmark, and I'm just going to add some annotations, right? So on the left, you have the latency seen by a serverless function. So you have a serverless function which accesses a database. And then on the right, you have latency seen by the user, so from the browser perspective. And the global and regional are really confusing. So global means that they pick the closest by edge location to run the function, and regional means US East, right? And this is actually a really great definition. So I was talking to one of the directors at Equinix and asked, like, so what is edge computing from your perspective? And he just said that, you know, cloud computing means your database is in US East 1, that's where everybody puts it, and edge means it's, you know, wherever location is close to you, or like anywhere basically. So this is a traditional cloud database, and we can see the funny bit here is that, well, so the obvious one, of course, is that on the left, the regional, so basically US East 1 serverless function has, you know, relatively low latency to the database, which is running on US East 1. If I pick a closest by edge location to run the function, so now it actually is super slow, of course, because now the compute is geographically distributed. But the really sort of important part is on the left. As you can see, there is no difference if I use edge or not, right? It is slow anyway. And the reason is because we didn't actually eliminate any geographical latency, right? Because if your function runs in US East, it will have low latency to the database, but you will have high latency to the function. If the function runs close to you, you will have low latency to the function, but the function will have the same low latency to the database. So what if we had an edge database which is replicated to these different edge locations, right? And basically, the key bit is that on the left, there's a lot of variability, by the way, in the latency. But nonetheless, it is more or less the same access latency, regardless of which function you picked, you know, the one that's close to you or one in US East, because the data is still there. But the actual advantage to the end user, so latency seen by users on the right, now you see what you should see is if I pick the global one. If I pick the closest edge location to run my compute, I have lower latency than going to the US. So 2 times lower latency roughly. Right. Basically eliminating the geographical latency. So that's about edge. And I seem to have been really quick because I don't have a lot of slides on Sky Compute. Any questions so far?
Yeah, I could ask one thing regarding Azure. I remember a few years ago hearing about some Azure Edge or Azure Stack or maybe even both. And if I remember it correctly, they were technologies that allowed you to bring the hardware or some sort of hardware with you to some place where there is not necessarily a network connection, and they could do some sort of pre-processing with your data that you collect, for example, with IoT devices. And when they do connect to the cloud, then they can push it there and continue processing further. So do you see these sorts of technologies coming up, or what is your take on these?
So I'm not aware what Azure provides. So sorry, I don't have an opinion. There's also so internally I know that Azure, for example, uses FGPAs and they also actually even Google does their own chips because they just, you know, of course try to optimize every bit out of that. Like for example, load balancers and stuff like that could be basically hardware stuff, but I don't know about this custom stuff. So final topic.
Actually, I have one question related to that. In relation to like cloud, not cloud, sorry, the edge databases, like what's the practical use case for it? Because my initial thoughts are essentially like, could I have the like application database be that close? But then how do you handle syncing? And then second is like caching. And then I wonder, what's the point? Why wouldn't I just use something like Redis or something like that?
So twofold answer. So why do you use edge functions? So these are typically latency sensitive things like you do A/B testing or personalization. E-commerce platforms let you run your code in the, like, you know, I'm not going to name any specific ones, but you create an online store using an e-commerce platform, but you want to customize some bit, right? And now you have actually the latency requirement of, because the platform wants the experience for end users to be fast. So, that's why you don't have usually a database there. Why wouldn't you use caching? Well, essentially, I think Redis is a cache. Like, it's a key value store that's super fast, but essentially used as a cache. So the reason why we are doing what we're doing is we just bring the database, and you don't have to worry about the, invalidating the cache. You can do the full SQL queries. If you don't want to use SQL, use an object relation mapper or query builder. Basically, you can do these more complex queries directly in the application. So sort of simplifying it, if that makes sense. But as I said, like the caching and key value stores are things that people use, but there are downsides too. And they're super fast, by the way. But there are downsides in terms of what can you actually do with them, because you need to now recreate sort of the data model that you need from your application to put into the Redis, for example, and also do the invalidation. Hopefully it answers your question. So Sky computing, and then let's wrap up. So infrastructure above the clouds. So computing as a utility. So basically, what it means is computing would be like electricity, like you plug into, and you get the electricity in the same way you would get computing, right? And this was one of the sort of visions of cloud computing. Well, so I'm just going to say it. So computing as utility is a model where you provision and use compute on demand and pay for what you use. And cloud computing, that was one of the sort of big visions. But the reality is what we ended up with is basically multiple vendors with fragmented APIs, right? So my take is that maybe cloud computing is more of a data center for rent. It's more than that, of course, but it doesn't really. We're not really at the level of where you can just plug your application into something. Even with serverless, you have the same issue because the APIs are fragmented, as we saw with the Cloudflare and AWS example. So Sky computing is an emerging paradigm, mostly in the academia, I should say, to bring this computing as a utility paradigm to reality. And the current proposal for Sky computing model, what you would do is essentially something like a multi-cloud with a compatibility wrapper. So you would use an API which basically is common to all. Which all of the cloud providers implement in one way or another, either natively or with compatibility. And there are some interesting parallels to what happened with Unix development in the 80s. There was a period of time that was called the Unix Wars, because you had a lot of incompatible Unix variants basically, and you couldn't portably run your applications. And which is why they invented something called POSIX, which is a portable interface, and then all of them converge. But with Sky computing, the situation is of course different. There is no common ancestor. Like in the Unix case, everything starts from the original Unix, and then they fragment. But in this case, we really have completely different platforms. So the challenges are who would define the APIs in Sky computing. Right, will developers actually use the compatibility layer, and how would you get the cloud providers to participate in Sky computing? Like, why would Microsoft and Google and Amazon agree that let's just do these APIs? And one of the reasons that we have fragmented APIs is because every provider wants to basically provide something different, something that the others don't provide. And that's it for Sky computing. So to summarize, so there are overlapping paradigms that move us beyond the cloud computing model, which maybe is more in the past. So serverless computing aims to break free of the machine abstraction. Edge computing, on the other hand, aims to move computation and maybe state closer to the user. And finally, Sky computing aims to sort of fulfill the vision of computing as a utility. And that's it.